All right, it's finally time to do some problems. This is part 3 of chapter 7, Gravimetric and Combustion Analysis. Let's get started. All right, the first gravimetric calculation we're going to perform looks pretty scary, but actually is as easy as a problem in general chemistry. All we have to do is relate the mass of the precipitate to the mass of the original analyte, which that's done with a balanced reaction and moles to moles. Anyway, let's read the problem. So it says, in one experiment, 0.3216 grams of sample was dissolved in 25 mils of acetone and 1 mil of acetic acid was added. After 5 minutes, the precipitate was filtered, washed with acetone, dried at 110 degrees Celsius, and found to be 0.7121 grams. Find the weight percent of piperazine in that commercial material. All right, so this seems like a lot of fluff here that we don't need. Basically, what they want to know is what is the content of piperazine in that impure commercial material. And you can find that out if you know the mass of what you weighed, right, of the actual product. The product was found to be 0.7121 grams. And you have the balanced chemical reaction, so all you got to figure out is just go back to piperazine and figure out the grams that the original analyte gave, and then divide it by the actual weight of the sample, which they gave it to you at the beginning. It's 0.3216. So let's just do it step by step. First thing we need to do is find the mass of the piperazine. Like I said, the experiment gives you the mass of the product, which is 0.7121. So you take 0.7121 grams of the product, and you use the molecular weight of the product, which is they give it to you, to get 2 moles of the product, right, which is 206.240 grams of product is equal to 1 mole of product. Now you go moles to moles. It's a 1-to-1 ratio, so 1 mole of product goes to 1 mole of piperazine. Now all you do is convert that to grams of piperazine by using the formula mass. So 1 mole of piperazine is 86.136 grams of piperazine, which gives you 0.2974 grams of piperazine. So basically you're done, because you already have the grams of the substance. Now you just need the grams of the sample. The grams of the substance is 0.2974 grams divided by the 0.3216 grams of the sample times 100 gives you 95.14%. Easy peasy. We will go ahead and do more of these in class, but now I want to talk about when the stoichiometry is actually not 1-to-1. It's just as simple. You just have to use the balanced equation. Let's try one. The problem reads like this. Solid residue weighing 8.4448 grams from an aluminum refining process was dissolved in acid to give aluminum 3+ in solution. The solution was treated with 8-hydroxyquinoline to precipitate 8-hydroxyquinoline aluminum, which was ignited to give aluminum oxide weighing that much, 0.8554. Find the weight percent of the aluminum in the original mixture. This problem is exactly like the other problem that we did. The only difference is that it's now not 1-to-1 mole ratio. So you get the sample product that they weighed, 0.8554 grams of aluminum oxide, and you know the molecular weight of the aluminum oxide, so you take grams to moles of aluminum oxide. Now for every 1 mole of aluminum oxide, there's how many moles of aluminum? 2, right there. So you take those 2 moles of aluminum oxide and take it to grams with the formula mass, which is 26.982. If you do all that, you should get 0.4527 grams of aluminum. Now, the only thing you have to do to find the weight percent is, of course, put the 0.4527 grams of aluminum divided by the solid residue, the mass of the sample, which was 8.4448 grams of the unknown, and then times it times 100. And you'll see that you should get 5.361%. So these are really simple. They're exactly like what you used to see in general chemistry. So these shouldn't give you any problems whatsoever. Now I want to do a little bit more complicated problem. Complicated in the sense that they're going to give you a lot of information, and you, as always, need to just figure out what you need and how to get to the answer. All right, it's really long. As a matter of fact, this is not even the entire problem. It's continued onto the next slide, so just bear with me. This, by the way, is on page 157 of your book if you want to read it with me. To measure the nickel content in steel, the steel is dissolved in 12 molar HCl and neutralized in the presence of citrate ion, which binds the iron and keeps it in solution. So first, let's think about that. They want to measure the nickel content that's in steel. So what they do is they add 12 molar HCl to neutralize it and bind the iron. So they bind the iron out of the solution so that the nickel that's left is in solution and you can use it, you can react it with something else. So it's available to be analyzed. So basically they take out or they bind what they don't want so that they can go ahead and add something else to analyze what they do want. But anyway, okay, so the slightly basic solution is warmed and dimethylglyoxime, DMG, is added to precipitate the red DMG nickel complex. The product is filtered, washed with cold water, and dried at 110 degrees Celsius. So again, they've got the steel that they dissolve into an acid, a strong acid, and they neutralize it in this ion, presence of this ion, and then that 12 molar HCl binds the iron and keeps it in solution. What's left, what's not bound, is the nickel. After they have that nickel in solution, they go ahead and add this DMG, which is this molecule right here, to react with the nickel so that then they can precipitate out this blue molecule right here, which is the DMG nickel complex. Okay, so that's the background information. Now, the real question becomes, if the nickel content is known to be near 3 weight percent and you wish to analyze 1 gram of the steel, what volume of a 1 weight percent DMG in alcohol solution should be used to give a 50% excess of DMG for the analysis? And then they give you the density of the alcohol solution. This is really a lot of information, so let's read it again. If the nickel content is known to be 3 weight percent, so that means they know that the nickel in steel, it should be about 3 weight percent. Okay, so that means if they want to analyze 1 gram, only 1 gram of the steel, if it's 3 weight percent, how much nickel do you have? Well, that would be 3 weight percent means 3 grams of nickel over 100 grams of nickel, which is times 1 gram of sample, right, which would be 0.03. So you have around 0.03 grams of nickel in this sample that you want to analyze. Okay, what volume of that DMG, which happens to be 1 weight percent, do you need to use to give a 50% excess of that DMG for the analysis? Okay, so we figured out how much nickel we have in this, supposedly how much nickel we have in this steel sample that we're going to analyze, and it happens to be 0.03 grams of nickel. I'm going to go ahead and go back to this slide so we can see the reaction. So we have a 0.03 grams of nickel. We're going to go ahead and convert grams of nickel to moles of nickel, because remember, we always go to moles. And you see here that in 1 mole of nickel, there's 2 moles of DMG. So go ahead and convert that to grams of DMG, because that's really what they want to know eventually. They want to know how much volume, right? How much volume of this DMG do I need to add to this solution to get to the answer? So now you're in grams of DMG. So basically, you've already arrived almost to the end of the problem because you figured out how many grams of DMG you need. But remember, now we look back and we notice that the problem said, I want to know how much volume of this 1 weight percent. So now they give you extra information. Okay, so you have the 1 weight percent of this DMG, and then they want you to figure out how much you need if you wanted to get 50% excess of DMG. That's a trick. You probably have never seen this before, but so you've got the grams of DMG that you would need, but that's if they wanted to know a 1-to-1 ratio. They want to know a 50% excess. So whatever answer you get, which should have been 0.12 grams of DMG, you go ahead and multiply that times 1.5. because they want 50% excess. If it was just they wanted to know 100%, it would be times 1, but since it's 50% more than 100%, you do 1.5. So that'll give you 0.18 grams of DMG. So that's how much you need to add to this solution to analyze 1 gram of steel. The next thing you need to do is, since you know the grams that you need to add in there, you gotta connect that with, okay, well, what's the concentration of this weight percent of this solution that you're putting in there, right? Of the DMG. The DMG happens to be 1 weight percent. So you go ahead and take the 0.18 grams of DMG, multiply that times the weight percent that they're telling you it's 1 weight percent. So that would be 1 gram of DMG over 100 grams of solution. And then now you can kind of tell the end, right? The final end point is they wanted to know how much volume of this 1 weight percent DMG do I need to add. So you use the density. The density will go ahead and cancel out the grams of solution and give you the milliliters of solution that you need. That ends up being 23 milliliters. So you need to add 23 milliliters of this 1 weight percent DMG solution to analyze 1 gram of steel for nickel, and knowing that nickel is around 3% in steel. Actually, this problem is a great problem because it really gets you thinking, and it kind of makes you hopefully understand percents, weight percents, and how to go back and forth from a reaction, okay? And it's a different type of problem because I'm pretty sure none of you have ever done anything like this, but don't, like as I always say, do not freak out. This is something that if there's more problems like this, there's more examples. So if you just keep doing it, you should be able to get it. This is the end of this video. I have one more video which is going to talk about combustion analysis, and we're going to do some problems on that. And we will be done with chapter 7. All right, guys, see you later.